Yeah, until you get to the two level control, and then they're both normally closed. What's that? Just about all of them. Well, the Doppler is not electromechanical because that's totally electronic. Time of flight is not electromechanical. The paddle wheel, the turbine, uh, so the first ones we went over were electromechanical. Let me bring up the yeah. So the Doppler and the time of flight, those were totally electronic. There was no mechanics to that, right? Yeah, ultrasonics. Um, and then we had the paddle wheel, and then we had the turbine, then we had the vane, one that actually pushes back on a vane, which is very, very popular. Those are not electromechanical either. It depends on what they use as a sensing element. So yeah, differential pressure. So what measures the differential pressure? So those so the ones that were basically electromechanical were let me bring that up. That was flow, right? So this would be electromechanical. The spring and piston would be electromechanical, right? So it's got a spring. This would be probably not an electromechanical. It depends on what the actual pressure sensors are. So what we're yeah. And then we have the Ventura, which works basically the same way as the orifice, except this doesn't create as much turbulence flow. And this would be definitely electromechanical. No, this is a PI static. Uh, so this PI static could be electromechanical, but we don't know because it's whatever sits in the pressure, right? You understand? Yeah. Well, it could be, but it couldn't be. This wouldn't be. This is definitely electromechanical. Are we okay? So we can't. Those wouldn't be on there because they could be what? Either way, it depends on what's sensing the pressure. This would definitely be electromechanical, which is a vane, and of course paddle wheel. This would be electromechanical, right? And then the turbine. This would be electromechanical. This would be totally electronic for sure. Magnetic flow sensors. Ultrasonic. This would be totally electronic. Doppler, time of flight. These would be totally electronic. Some of them are gray area. It depends on what you're actually using to sense the pressure differential. That makes sense? Okay. No, what normally open or normally closed. So heat would be a normal heating system. So what do we want it to do? We want it to come on when the temperature drops down, right? Heat, we want it to, cooling, we want it to turn on when the heat gets up too high, right? Understand? Okay. So it runs until the temperature gets up so high, and then it's open. And that makes sense? Okay. Any more? Yeah, and it also what's nice about an AC motor is that it gives us two things. It gives us a frequency that's proportional to the speed, and it also gives us a voltage that's proportional to speed. So we have two things that we could look at off an AC tach. That makes sense. A DC tach would be a voltage proportional to the speed, both on frequency and voltage. And I could hook that up and show y'all again, but can't get frequency from direct current, right? Of course, on newer plants, you'll probably have encoders. On your older plants, you'll probably have DC tachs or AC tachs. What's nice about encoders is we can bring those into a high-speed counter on the PLC, and we don't have to have any additional hardware. If we have a DC, then our PLC would have to have an analog to digital converter built into it. So any more? What's that? Load current is the amount of current required when the load is energized, right? So of course we yeah, minimum holding would be the amount of output on these digital sensors. You can't have no load on them for it to operate. So we have what we call a minimum holding current. So if your load does not pull a minimum amount of current, then the sensor is not going to work. What's required to make the sensor operate, huh? Yes, that's required to detect a target, but I don't think it's written like, I don't think it was actually written like that. Yeah, to develop the sense and feel. So it's how much current's required to make the sensor work, right? You understand that? This really comes into play when we're dealing with electronic sensors. And the problem we have is and this really comes into play with two-wire sensors, the one that actually powers up off the load. Now, we can get by with a two-wire sensor on these 120-volt sensors. Everybody understand why? We can get by with a two-wire sensor on a 120-volt system. Yeah, it's in series, but we can afford to get a voltage drop. So I think most of y'all's dropped around 6 volts. Well, still that still left 115 volts to operate the sensor. If this was a 24-volt supply, then like most of y'all use now, because what's the big advantage of 24 over 120? Yeah, we don't have to wear all that PPE to work on these PLCs. but we can't afford a 6-volt drop when we're only dealing with 20 volts, right? So these would come in and we would have a 3-wire sensor. So here we don't really have to worry about the operating current because this guy powers up directly off the line, and I've created a short circuit and nobody caught me on it. So this one, we usually don't have to worry about the operating current. This guy right here, we do. It powers up through the load. So that means if this is a real high resistance load out here, then these guys here might not work because it might not do what? It might not get enough current flow through it to develop that 4-volt voltage drop that's required to get the power. That 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 uh, that operating current is really, really critical on these guys. Okay. So load current is actually the amount of current pulled by when the output of the sensor goes true. It's the actual amount of current that's required by the load. And this is very important too because if you have a real low resistance load out there, then you can cause big problems, right? You could literally burn your sensor up. So that's where we go. If we're going to run a real low resistance load, then we're going to have to go through like a control relay. So any more questions, guys? So we're okay on those different currents: load current, operating current, um, minimum operating current. Is it minimum operating current or whole current? I can't remember. Holding current. So the current's got the load's got to pull some current, right? Then it's got a maximum current, which would be the operating current. It's got the operating current, if I said that twice. So any more questions on the review? So we're just going back over the review to. Oh yeah, I actually found a picture. So basically, the way the fuel indicator on your car works, it's just got a float out there, and it's hooked up to a potentiometer up here. And of course, the problem y'all been having is when we come up here and we set a span. So normally, when we come up here and so a good example is we usually power up a PLC. So standard power for PLC now is 24 volts. Analog, so that means we have a 24 volt supply out there. Standard inputs for analog on PLC is 0 to 10 volts. So we got a big problem, right? You understand? And if I try to power it up the analog devices off my 24 volts, we're either going to burn them up or we're going to put more than 10 volts. So what we have to do is we literally have to set the span of this pot. So the way we set the span is we come up here and we put a series resistor in series with the pot. So if that was a 10K pot and I want plus 24 volts up here, and what do I want on my A to D input? I want 0 to 10 volts. Then what size would that resistor right there be? Ohm's law, guys. Well, I want this bottom resistor, which is a 10K, which is a pot. Y'all got to understand a pot. A pot always has this value between 1 and 3. We vary it with this thing, but when we say a 10K pot, that means if I measure between 1 and 3, it would measure 10K. So what happens is that this guy, this over here has a real high, we talk about loaded, but what we're doing is we're assuming this over here almost has infinite resistance, so it don't affect it. So your input, your analog input on your PLC, somewhere it tells you what that resistance value is. It's on the range of electric. So 10 comes over here and 10K over here, it's not going to affect the pot enough to cause any problems with our calculations, right? So I know this is a pot. I want to get 10K out of that. I mean 10 volts out. So that means I want 10 volts right there. So if I put 10 volts right there, then what I do is that this pot can give me between 0 and 10 volts, which would be great for the analog input on my PLC. But powering this thing up with what? 24. So what I'm going to do is I'm going to use a what? I'm going to use a series dropping resistor. How much voltage do we want that resistor to drop? Huh? 14 volts. Okay. So 14 volts. What size would the resistor be? Well, it's a series circuit. I know two things about this guy down here. I know the size and I know the voltage, right? So what can I calculate? Okay, so I would be equal to what? 10 volts divided by 10K. So what would my I be? It can't be 1K. You can't divide 10 by 10,000 and come up with 1K, right? 1 milli, maybe. You understand what you're doing, Brian? No, you can't take 10 divided by 10,000. Okay, so this guy up here, I want this guy here to drop what? So R is equal to what? What's that? R is equal to what? That's the size resistor I put it there. So what we've done is we set the span, the range of the pod. So I don't know what your engine control module does on your car. What voltages they use out there? Well, you know, what car we're dealing with basically what's the voltage? No, well, could get that high. We say 12, but it gets up to 14. Yeah, a little over 14 when it's running. So we got to have some type of regulator in there. So 10 volts would probably be about right. Huh? 10 volts on the fuel indicator. Because you wouldn't want it. So what we'd do is we'd have a regulator in there that would regulate at a voltage below. It's going to have to be below 12 because 12 is guaranteed, right? Okay. So 12 is guaranteed. Could be higher. What's that? Well, my span would be what? Would be from 0 to 10 volts. And that's kind of bothers me too because, you know, we have 12 volts up there and then you have a resistor and you say we're going to get 12 volts out of here when you know that would say that resistor is dropping no voltage, right? You understand that? So you know as soon as you see that resistor right there, you know it's got to be less than what? Whatever's up there. It's got to be less. Got to be less. Can't be more. Got to be less. Because if you say it's dropping, I think the question said 12 volts, and then they had a resistor up there. The speed? I think I pulled the stage sensors up. So this guy here gets us 21 pulses per revolution, right? But the one on the test only gives us what? 4. So you take the time. Everybody okay on measuring time on an oscilloscope, right? Then you multiply it by the number of pulses you get per revolution, right? Then we take the reciprocal. So this is time. We take the reciprocal of it, so it gives us frequency. But this is going to be revolutions per second because all this down here is seconds, right? And then what we do to get it in revolutions per minute. So this 2100 is not the one you're going to use. What's this right here? Pulses per revolution, right? So this guy gives us 2100 pulses per revolution. The one on the test only gives us 4. Everybody understand that? And that would be the number of blades. So if you look down on the test, it's got 4 blades. We give you the time for 1, and then you multiply by 4 to give you the time per revolution, right? You understand? Seconds per revolution. We take the reciprocal of that. That would give us the RPM per second, and then we multiply that by 60 to get the revolutions per minute, which is an international standard for measuring speed. And this is becoming the preferred method of indicating the speed of a motor, because if I use one of our analog if I use one of our analog speed sensors like a DC tachometer or an AC tachometer, we're going to have to take an analog value and convert it into a digital for the PLC. Here we could bring this thing directly into the PLC and we could count it per revolution, right? High-speed counter. You can't use the software counters. They won't keep up with these encoders. But high-speed counters would be, so you have to research those things a little bit. So just about all these PLCs have hardware-supported counters. We call them high-speed counters now to keep up with these guys. So the math is a little easier on a high-speed counter. You can just count the number of pulses per revolution and divide it by the number. So the math is a little easier. Any more questions? It's going to be on the test, on the review. You don't know what's going to be on the test, but the review. Right now we got it, yeah, today. Right now we have it scheduled for next Monday. And the problem with scheduling it for next Monday is you only have one class to study for test 3. We do have an option of moving it, since we're through with our lectures, we do have an option of moving it to this Wednesday. It's your call. But if we move it, if we move it to this Wednesday, that'll give you the whole weekend to study for the final. No. Not unless you want it. Not unless you want to. We can do it today too. But it wouldn't take me a little while to get ready for today. Okay. Vote, vote, vote. Okay. Of course, that means you got to get through with PT previous test too for Wednesday, right? Some people already did it, but only 2 people in the class would. Yeah, you would like that, wouldn't you? And that would be. And what it does, it'll give you a whole week to not only. So normally, what we do is we want y'all to have PT1 and PT2 through here, but this will give you all weekend to study. Go back and study all 3 of them. And what it also do is it'll give us, in, uh, if we give it Wednesday, we can give it at the end of the class, and then we can go over the test on Monday. No, we'll need to go over this because I need to make that available. So we'll go over the test. So the test is going to be scheduled at the start of class. I'll send out y'all a text Wednesday, this Wednesday. And then the final day, next Wednesday. And then, by the way, they want us to bring up registering for spring term. You'll need to go ahead and do that. Even if you don't pay, you need to go ahead and pre-register for the classes. Spring term starts January the 9th, I think. They're going to go ahead and pre-register for the classes that are intended on taking. So any more questions about what's on the review? Huh? Yeah, we'll be in lab the rest of the day today. Then we'll take the test to start the class on Wednesday. Then we'll be in lab after that. And then we'll be in lab all day Monday. And then we'll come in and take the final exam on Wednesday. Yeah, I need to find that out, guys. Undoubtedly. First 2, yeah, okay. I'll look. Need to make myself a note. See if I. Yeah, hold on. Everybody got this? Yeah. No, you can't. It's not this until I get them sorted out. This is the lactone temperature sensor. Yeah, it's plus the supplement you can get to keep, right? There they are. Y'all get these. Go to the lab. Y'all don't have any more questions about what's going to be on test.